In this video, we're going to continue our discussion of top-down parsing algorithms with another strategy called predictive parsing. So predictive parsing is a lot like recursive descent. It's still a top-down parser, but the parser is able to predict which production to use, and it's never wrong. The parser is always able to guess correctly which production will lead to a successful parse, if any production will lead to a successful parse. And it does this in two ways. First of all, it looks at the next few tokens, so it uses look ahead to try to figure out which production should be used, so based on what's coming up in the input stream. But also it restricts the grammars. So this only works for a restricted form of grammars. And the advantage is that there's no backtracking involved. And so the parser is completely deterministic. It will never try alternatives. Now, predictive parsers accept what are called the LLK grammars. And this is a really cryptic name, and so let me explain it. The first L stands for left to right scan. So that means we're starting at the left end of the input and reading left to right. And in fact, that's what we always do. So all the techniques that we look at will have an L in the first position. The second L stands for a leftmost derivation. So we are constructing a leftmost derivation. That means we're always working on the leftmost non-terminal in the parse tree. And K here stands for K tokens of look ahead. And in practice, while the theory is developed for arbitrary K, in practice K is always equal to 1. And so in fact, we'll only discuss the case K equals to 1 in these videos. To review, in recursive descent parsing, at each step, there may be many choices of production to use, and so we need to use backtracking to undo bad choices. In an LL1 parser, at every step, there's only going to be one choice of productions, of possible production to use. And what does that mean? Well, it means that if I have an input string, if I have a configuration of the parser where I have some terminal symbols omega and a non-terminal A, possibly now followed by some other stuff. There could be terminals and non-terminals, but again, A here is the leftmost non-terminal. And the next input is a token T. Well, then there is exactly one production. A goes to alpha on input T. Okay, there's only one possible production that we can use. And any other production is guaranteed to be incorrect. Now, it can be that even A goes to alpha won't succeed. It could be that we will be in a situation where there's no production we could use. But in an LL1 parser, there will always be at most one that we could use. So in this case, we would choose to rewrite the string to omega alpha beta. Let's take a look at our favorite grammar, the one we've been using for the last couple of videos. We can see an issue here with using this grammar for a predictive parser. Take a look at the first two productions for T. They both begin with int. And so if I tell you that the next terminal in the input stream as we're parsing along is an integer, that doesn't really help you in trying to distinguish between these two productions and deciding which one to use. So in fact, with only one token of look ahead, I can't choose between these two productions. And that isn't the only problem, actually. So we have the problem with T, but the same problem exists with E. We can see that here, both productions for E begin with the non-terminal T. And it isn't really clear what we're to make of that, because T, again, is a non-terminal, not a terminal. So how would we even do the prediction? But the fact that they begin with the same thing suggests that it's not going to be easy for us to predict which production to use based on only a single token of look ahead. So what we need to do here is we need to change the grammar. This grammar is actually unacceptable for predictive parsing, or at least for LL1 parsing. And we need to do something that's called left factoring the grammar. So the idea behind left factoring is to eliminate the common prefixes of multiple productions for one non-terminal. So that's a mouthful. Let's do an example. Let's begin with the productions for E. And we can see again that both productions for E begin with the same prefix. And what we're going to do is just factor out that common prefix into a single production. So we're going to have one production where E goes to T, and then we're going to have multiple suffixes. So let's introduce a new non-terminal X that will handle the rest. So here we have E goes to TX, so it says that everything that E produces begins with T, and that's consistent with these two productions. And now we have to write another production for X that handles the rest. And what would that be? Well, one possibility is that we're in this production, we need to have a plus E, and then in this production there's nothing. So that's easy to handle. We write one possibility for X is that it goes to plus E, and the other possibility is that it goes to epsilon. And now you can see the general idea. We factor out the common prefix. We have one production that deals with the prefix, and then we write, and we introduce a new non-terminal for the different suffixes, and then we just have multiple productions, one for each possible suffix. And you can see what this is going to do. This is effectively going to delay the decision about which production we're using. So instead of having to decide immediately which production we're going to use for E, here in this grammar, we wait until we've already seen the T, whatever is derived from the T, and then we have to decide whether the rest of the production is a plus E or the empty string. Let's do the other set of productions. So we have T goes to, and now the common prefix is int that we want to eliminate. So we're going to have just one production that begins with int, and then we'll have a new non-terminal to stand for the various possible suffixes. And now here we also have another production that doesn't have anything to do with int, and so we just leave that one alone. That production just stays here. Because it already begins with something different, we won't have any trouble predicting between these two possible productions. And now we have to write the productions for Y. And again, we just take the suffixes of the productions that we left factored and write them down as alternatives. So one is empty and the other one is times T. So we wind up with times T or epsilon. So here's the left factored grammar now typed out neatly. And we use this grammar to construct a parsing table. And let's not worry right now about how we got this table. I'm not going to give the algorithm right now. But let's just say that we got it somehow. And what I'm going to explain is how we use the table. So one dimension of the table is the current leftmost non-terminal in the parse tree. So that's on the rows. And then the columns represent the next input token. So the next token in the input stream. And then the entry is the right-hand side of the production to use. So which production that we should use at that point in the parse. That's the production that's predicted. So let's do an example. So let's look at the eInt entry. So this entry right here. And what this says is that when the current non-terminal is E, meaning the leftmost non-terminal in the parse tree, and the next input is int, the thing that we see coming up in the input is an integer, then we should use the production E goes to TX. So we should expand E with the children TX. Let's do another example. So when the current non-terminal is Y and the current token, the current input is plus, then we should use the production Y goes to epsilon. Okay, what that says is, it's a little bit different situation than the previous one. It says, look, when you see a plus in the input and your current leftmost non-terminal is Y, the only way this parse is going to succeed is if the Y doesn't produce anything. You need to get rid of the Y and move on to another non-terminal, whichever one is leftmost after you get rid of the Y, if you want to have any hope of parsing this particular string. And finally, notice that a lot of the entries are blank, and those are error entries. So let's take a look at the E star entry. That says that if the leftmost non-terminal is E and the next input token is a times symbol, a star, well, then there is no move that you can make. There is no production you can use for E that's going to successfully parse that input, and this is the point at which you would raise a parsing error. In the rest of this video, I'm going to give the algorithm for parsing using a parsing table, and then in future videos, we'll explain how to construct a parsing table. So the method for parsing using a parsing table is similar to recursive descent, except that for the leftmost non-terminal S in the tree, we look at the next input token A. And then, as we just illustrated with the examples, we look up in the table the production to use at the entry S comma A. And instead of using recursive functions to trace out the parse tree, we're going to have a stack of records that can record the frontier. And so at any point in the parse tree, we will have some non-terminals that have yet to be expanded. Those are always at the frontier, at the current leaves of the parse tree. And also there are some terminals that we have yet to match against. And those will all be recorded on a stack. And the important property of the stack is that the leftmost pending terminal or non-terminal is always at the top of the stack. So either the terminal we're trying to match or the non-terminal we're trying to expand will always be on top of our stack. We'll reject if we reach an error state. So if we look up one of those empty entries in the table, we will reject the string. And we'll accept if we reach the end of the input and we have an empty stack, meaning we have no pending unmatched terminals or unexpanded non-terminals. So here's the algorithm. We initialize the stack to just the start symbol S and the special symbol $. And $, is not part of the alphabet, or you could think of it, we extend whatever our alphabet is with a new symbol called $. $. Marks the bottom of the stack, and you can think of it also as marking the end of input. So this is just a way of recording where the end of the input is going to be. Okay, so once we've matched something against S, then whatever is left had better be at the end of the input. That's what that stack expresses. And now we're in a loop, so we're going to repeat the following moves until we can't repeat them anymore, until the stack is empty. Okay, and there's two possible moves. Let's do the terminals first. So let's say the top of our stack is a terminal. So here we're dividing the stack into the top of the stack and the rest of the stack. So what are we going to do if the top of the stack is a terminal? Well, we're going to try to match the input. So we're going to say, well, at the top of the stack, the terminal on top of the stack matches the next thing in the input. Then we advance the input, and we pop the stack. So we have successfully matched the input against the terminal, and so that terminal is done, and we should progress into the stack and match the next thing that hasn't been handled yet. And if they don't match, if the terminal that we're looking at doesn't match the next thing in the input, well, that's an error. We don't have any backtracking here. There's no way to parse the string, and so we'll raise an error. Now, the second class of moves deals with the non-terminal. So let's say that the top of the stack is a non-terminal X. And remember that the top of the stack will be a non-terminal exactly when that is the leftmost non-terminal. So now what we do is we look at our parsing table under the entry for X and the next input symbol, and that should give us the right-hand side of a production. Okay? And now what we do is we pop X off the stack, and we push the children of X in the parse tree onto the stack. So this is the way we expand X. So now the leftmost unhandled thing in the parse is going to be Y1, because that's the first child of X. And then all the other children of X are next, and then whatever else is in the stack. And again, if there's no entry for the current non-terminal and input in the table, then that's an error, and the parsing stops. So let's work through an example using our parsing table. And you might want to refer back to the parsing table. I have not included it here because there isn't space for it. But I'll work through it, and you can go back and look at it at some point and convince yourself that I made the right moves. So initially, our stack is $. So E was our start symbol, and $, is our end of input symbol. And our input, we're going to try to parse the input int times int. That's what we want to parse. And then, of course, we have our new symbol $. We'll tack that on to the end of the input. And if all goes well, the $. On the stack will match up against the $. At the end of the input. Again, $. Here is just a way of marking the end of the input and expressing that we need to parse the entire input. And so now, if you look up the E int entry, so the first terminal in the next terminal in the input, and the leftmost non-terminal in our parse, you will see that the action we're supposed to take is to use the production e goes to tx. And let me over here at the same time construct our parse tree. Okay, so initially our stack, again, the stack is the frontier of the parse tree. Initially, all we have is the root of the parse tree, and that is its own frontier. It's just one symbol. We haven't processed it yet. And so E is on the stack. E is unexpanded in the parse tree, and now we're going to use the production E goes to Tx. So we'll have T and X added as children. What happens next? Well, E is popped off the stack. T and X are pushed onto the stack. And now notice the frontier of the parse tree is Tx. These are the unprocessed leaves, either unmatched input or unexpanded non-terminals. And in fact, the stack records exactly which one is leftmost. So T is at the top of the stack, X is below it on the stack. Okay, well, we still haven't consumed any input. And now if we look at the T int entry, it says to use T goes to int y. And so now we can expand T by int y. And now what's going to happen is T is popped off the stack, int and y are pushed onto the stack, and now notice the stack is int yx from top to bottom. The frontier of the parse tree is int yx. Okay? And now we have a case where we have a terminal on top of the stack, and so now we're going to try to match it against the first terminal in the input. And indeed they match, and so what happens is int is popped off the stack, and the terminal, the input pointer advances in the input. And here I've recorded that by just discarding the portion of the input that we've processed. So now we have times an int left to go, and the int has been removed from the stack. And so now what's on top of the stack is y. Y is indeed the leftmost unprocessed thing on the frontier. And the table says that for non-terminal y, on input times, we should use production y goes to times t. So let's put that in here. And now what's going to happen, y is going to be popped off the stack, times t is going to be pushed onto the stack, and now notice our stack is times t, x, and the frontier, the unprocessed frontier of the parse tree is times t, x. Okay? So now we have a terminal on top of the stack. It matches the next terminal in the input. So we pop the terminal off the stack, we advance the input pointer. Now we have t as our leftmost non-terminal. Int is the next thing in the input stream. And the table says, well, in this situation, we should use the production t goes to int y. What does that mean? That means t gets popped off the stack, int and y get pushed onto the stack. Notice that the stack is int yx, and the unprocessed frontier of the parse tree from left to right is int yx. Once again, we have a terminal on top of the stack. We match it against the next terminal in the input stream. They match. And now we have consumed all the input. $sign is the only thing left to go in the input, but our stack is not empty. Okay, and so at this point, what does that mean? Well, if the stack is not empty and we're out of input, then everything that's left on the stack had better generate the empty string. So we better be using only epsilon productions from here on out. And indeed, the table says that when y is our next non-terminal and $sign, we're at the end of the input, we should use the production y goes to epsilon. So y goes to epsilon, that means y just gets popped off the stack. Epsilon gets pushed on the stack. Epsilon is the empty string, so nothing gets pushed on the stack. And now we're down to x. And in the situation where x is the next non-terminal, $sign is, we're at the end of the input, so $sign is our next symbol. Then the table also says to use the production x goes to epsilon. And then what happens? Well, x gets popped off the stack and nothing gets pushed on because the production was x goes to the empty string. And now we see we have $sign on top of the stack, $sign in the input, and so we have emptied the stack, we have reached the end of the input, and so we accept. That is a successful parse.